All right, stream tracer enthusiasts, constant rate injections. We've talked about some of how you might design it. Let's talk about what happens in the field. Okay, so when we head out to the field, we will select our study reach, and we'll actually establish things like both the upstream and downstream monitoring locations that will bound our study reach, and we'll establish the mixing length. Now, while you may have done some recon ahead of time, you may have used some empirical equations to plan on that mixing reach. Again, my recommendation is that you use a visual tracer in the field. So this means something that you can see with the naked eye and is not going to interfere with your experiment. If your tracer is bromide, use uranine or rhodamine, easy visual tracers. If your focus is a rhodamine tracer experiment, bring some uranine along. If you're using both of those, my go-to is also a gallon of milk, which will dissipate quickly in a small stream and not likely affect your optical tracers. So we've got our study site selected. We've established the upstream and downstream ends. We trust our mixing length. Let's collect some background data. And we are specifically focused here on data that are pre-injection. We want there to be no concern that any mass that we inject into the system is affecting these background data. So as such, this should be done before mixing up, in my opinion, before you mix up your tracer in the reservoir, before there's any possibility that you accidentally spill it. So as we do this, we'd like to also establish an upstream site or an ambient site. And the idea of this purple X that I've drawn here is we want to know what is coming into our study reach prior to our injection. So if background levels change that might interfere with our tracer study, we need a site that's not impacted by our tracer where we can study this, where we can monitor this time series and know what the impact will be through the system. Now, if you're going to monitor with SONs, this is the appropriate time to get them started, to get them deployed, get data logging, and critically important here is we want to give them time to equilibrate. So many SONs have onboard thermistors to collect temperature, and or some of the sensors are temperature dependent, either using that thermistor data or the actual performance of the sensor, the way the circuit behaves will vary. So it's really important that we give our SONs time to equilibrate in temperature. If you have a handheld probe that you are moving from site to site to make measurements, the same thing applies. You should leave that stored in the water so that its temperature stays as close to the stream as possible. And you should always make sure that you have a steady temperature on it before you collect a reading. So perhaps we'll deploy our SONs at the 3 locations I've just circled in black. If we're doing all of this with grab samples, this is the appropriate time to collect and store all of those sites of interest. Again, doing all of this prior to even mixing up our injectate to ensure that these are truly background samples, that we're not moving tracer around because we spilled some on our boots and our boots are then in the stream near a different location. Time to mix up the injectate. So here's our study reach. And we are broadly focused here on the idea that we have a reservoir sitting on the stream bank. This could be an agricultural water tank, a trash can, a 5-gallon bucket. We've got a pump, and we're using that pump to deliver our tracer at a constant mass per time into the system. So critical to all of the analyses that we do is actually understanding how much mass of tracer, or how much mass per time, we are putting into the stream. With a slug injection, that's easy. You've weighed your mass out, you bring it to the field, that's what gets released. In this setup, it's a little different because it's unlikely that you know exactly, perfectly how much mass you will inject a priori, even for the simple reason that if you inject the entire reservoir, it's unlikely you'll get every last drop out of it. So what do we need to do? First, we need to weigh our tracer mass prior to heading into the field. So in the laboratory, we want to weigh out our tracer mass in quantities that we can work with depending on the logistics of our experiment. We want to know how much mass we have and dissolve it in a known volume of stream water. Typically for that reservoir, in my group, we often use large trash cans. And while you can buy it at the store and it might say that it's a 44-gallon trash can, that's seldom actually true. So our trash cans will have permanent marks permanent marker on the inside where we've actually either used a known volume of water or used a weighing method to basically calibrate our reservoirs. So we know when we fill it with water, this line is equivalent to 30 gallons, or this line is equivalent to 100 liters. We need to mix well, so making sure that our tracer is dissolved in the injectate solution and that it's not stratified, so it's not high concentrations at the bottom and lower at the top. And critically important here, I believe that you should be collecting samples of your injectate both pre-injection and regularly throughout the day. If everything works perfectly, if your upstream station truly is well mixed, this should be redundant data. However, if you've put your upstream monitoring site in a place that's not quite well mixed, if your injectate changes in concentration through the day because some of it falls out of solution as a precipitate, or because some of it adsorbs onto the side of your reservoir, or because it's a photolytic compound and it actually decays during the day, you need to know that. So in an optimal world, these samples are redundant. In the reality of how a field experiment goes, these are really important samples to have. They will be extremely high concentration, and you'll probably have to use some serial dilution when you process them in a laboratory. But nonetheless, these are important for us to document what we're doing in the field. Okay, we're ready. We've got our injectate. Let's get our pump figured out. We are going to use a pump of some variety to pull injectate out of our reservoir and ultimately to inject it into the stream. So shown in red is pulling water in. And what we like to do in my group is to take a brick, so my beautiful brick in orange there, and basically zip tie the injectate tube onto a brick so that it stays at the bottom of the injectate reservoir and that we know it's not going to accidentally move out. Plenty of times I've seen the vibration from a pump, a breeze, something accidentally getting tripped on, pull this intake out of the reservoir, and then your pump starts to pull air and your constant rate injection is no longer injecting. On the output side, you'll see that I've drawn this as a recirculating system right now. So our injectate is going into the pump and then it's being transferred back into our reservoir. We're going to set this up to recirculate for a few reasons. One is we want to make sure we get a constant rate of flow. So we want to let the pump warm up if there's any warm-up period to it, and we want to know that we're getting a steady in time discharge. We want to make sure we clear any air from in the line. So some types of pumps can airlock. So if a big pulse of air makes it into that intake tube, it can cause disruption in the pump and even potentially stop it from being able to pump fluid. So we want to clear any air. And this is also the time at which we're going to first measure the injection rate. And the simplest thing to do is take a large graduated cylinder, put your injectate solution, your pump, your hose into that cylinder and record the volume of water that you collect per 30 seconds or per 60 seconds. That lets you get at a volumetric flow rate. Take your graduated cylinder that's now full of injectate, put it back in the reservoir. And we'll often make that measurement a few times early before the experiment starts to make sure that the pump rate is where we want it. So this is your chance to adjust the actual flow rate of your pump. At this point, we know the flow rate of the pump. We have recorded the time at which we're going to start our injection. And we can take that pink tube and put it out into the stream. And again, we'll want to secure the injection, the release point with maybe by putting it underneath a rock or by zip tying it to a brick, some means to know that it's going to stay in the stream channel and in a consistent location through the course of our study. And you'll notice I'm putting it at the center of the stream because that will give us the best lateral mixing. Things to be doing during the injection. We should monitor the flow rate out of our pump regularly. If my injection is perhaps a 10-12 hour injection, we often do this every 1 to 2 hours. On a multi-day injection, I might do this every 3 to 6 hours. But the idea is to make sure we actually are delivering a constant rate to the stream. You'll see I've drawn here, 6 potential measurements of pump flow rate through the course of an experiment. Reasons that I have seen variation in pump flow rates are as follows. Some pumps compensate for voltage from the battery changing, others do not. So some pumps, as the battery voltage slowly decays through the day, the pump performance will decay along with it. Other times we see the head that a pump is pulling, that a pump has to operate under, changing. What this means in a practical sense is when your reservoir is full, it doesn't take so much energy to move that water up out of the reservoir. When your mixing reservoir is almost empty, you've got a lot more energy required to pull fluid out. So as the head changes but the pump power doesn't, fluid mechanics tells us that we should be getting a different flow rate through the system. Viscosity of fluids can change as things warm and cool on the course of a day. Tubes and pumps can clog or pull in small pieces of debris that don't fully clog them but partially degrade their performance. And pumps can drift, especially pumps where you have a manual setting, like a manual lever or manual adjustment. As that pump vibrates all day, those manual adjustments can move in terms of where they're actually set. Best practice at the end of the day, you should be taking that graduated cylinder and regularly measuring pump performance. Our protocol is to walk out into the stream upstream of that injectate. We take our graduated cylinder, we time 30 seconds of flow, we put the tube back into the water, and we dump that mass back into the stream and rinse our graduated cylinder 2 or 3 times. So that is a minor disruption to the idea of a perfectly constant rate injection, but it's worth it to me. We still have the same amount of mass going into the system. It's a minor disruption, and it lets me know that my pump is consistent. The second thing we might have to keep track of is our injectate. So over the course of an injection, it's possible that we can't mix one reservoir that's sufficiently large for our experiment, that we need to refill or supplement that reservoir. So consider this case where we might want to do a 12-hour injection, and after 6 hours, our injectate has gone down. Now, why couldn't we use a single reservoir? Potentially the inability to dissolve enough tracer, the pump flow rate had to be higher than we planned on, or we couldn't put our flow on a pump low enough. There's plenty of logistical reasons for this to happen. So our protocol is to mix in a second reservoir, so not the one you are pumping out of, but independently mix at the same concentration that you planned on initially. So the same mass per unit volume, and to basically refill that reservoir. So the reservoir with our brick that we were pumping out of is always the same, and we mix in a second reservoir and then put that into the one that's being pumped from. That prevents us from getting air in the lines. It makes the logistics slightly easier than trying to move around large reservoirs of water, which are heavy and prone to tipping. And it does serve the function of somewhat smoothing out any minor variations in your injectate because you're partially mixing new injectate with older injectate. Now, before and after we do this mixing, we like to measure both the flow rate of the pump and the concentration of the injectate. I think those are both mission critical to make sure that post hoc you actually know that you were delivering a certain amount of water to the stream. Finally, I'll just point out mixing. Our goal is that the injectate is always well mixed. If you've got relatively low concentrations, this might just happen for you. If you are nearing solubility limits, you might need to regularly or constantly agitate the tank so that your tracer isn't precipitating out onto the bottom of your reservoir. I've also seen people set up a recirculating pump in the reservoir. So take, for example, a submersible sump pump and basically power it up inside the reservoir so that it just it creates turbulence and continually mixes that reservoir. That's perfectly valid as well. That introduces a second failure point. So you need twice as many batteries, twice as many pumps need to not clog, but you also don't have to go back and manually mix that reservoir. So that's absolutely an option. Finally, perhaps the most important reason we would execute a constant rate injection is to get the spatial profile along the study reach. So what we want to do here is focus on the downstream monitoring location. You can see I've drawn the rising limb of our tracer injection there in green. And we want to know that the system is at the plateau. In other words, we've sort of passed this portion where we had a rising limb. We're past this shoulder, so to speak, and we've got a relatively steady, constant concentration at the downstream end. At this point, we want to start at the downstream-most point and work our way upstream, collecting a series of samples along the channel center line. Some folks will set out flagging ahead of time so they know exactly where those measurements are going to be. And if you want to collect multiple profiles, that's really a great idea. Other folks will do this in a more approximate way and then survey or measure post hoc where they were. Critically important, you have to know where you're collecting the samples relative to your injection point, and you want to be working from downstream to upstream. Now the logic here is that you want to stand downstream, collect a sample upstream of you, and that prevents any disruption from your walking through the stream, disturbing the stream bed from impacting your sample. Then we'll go out to the stream bank, walk up to the next sampling point, walk in, collect upstream of where we're standing, and so forth. By working in that direction, we ensure that the disruption that we create by being in the stream is not affecting the sample that we're collecting. I'll point out as well that I have us collecting samples co-located with our SONs. This is really helpful post hoc if you're using SONs or automated data collection because it gives you another point where you can benchmark the SOND-based measurement to a laboratory-based measurement. And I have us again collecting at that background or upstream location where we should be collecting a relatively coarse but a real time series to ensure that the background conditions in our system aren't changing. Finally, a word on monitoring. So if you've set this up in the way that I've been describing it, you've really got these three sites that you're collecting a relatively fine resolution in time. One that's always upstream of the influence of your tracer in purple, the upstream end in orange, the downstream end in red. What I would suggest is you should keep all of these stations recording until all of them return to a background condition. For example, it would be easy to say, we've stopped injecting, let's pull the upstream end of the study reach, which is fine unless there's a background variation that propagates through your system, and then you will have missed it because you've pulled the upstream end already. So I suggest that you leave those monitoring all until all of your sensors have reached some background condition again. And just a friendly reminder, you can never go back in time to collect extra data. And so I always like to err on the side of monitoring longer. In my most optimal study design, we would deploy any SONs and start collecting any background measurements, and we would collect a full 24 hours of background because that lets us get at any diurnal pattern that might be in the system. Then we would do our tracer experiment until anything we can do in the field, looking at a sonde, using a probe, visual inspection, until all of that returns to background. And then I would like to continue monitoring at some relatively coarse level at least for an additional 24 hours. There are plenty of times where even though my sonde or my handheld probe seems to be back to background, what I'm actually able to see in the lab is that I didn't wait until the tracer had fully passed the system. So sometimes our laboratory techniques have a higher detection ability than our visual inspection or our SONs. So optimally, you'll have 24 hours of pre-data, you'll wait until you believe everything to be back to background, and then maybe every 4 to 6 hours, you'll even collect a background sample for the next 24 hours, just to ensure you're really getting that late time tailing of your tracer from the system. All right, folks, I hope that this helps you get a sense of the things you should be thinking about, planning on performing when you're doing these field tracer tests yourself. Thank you very much, and you can check your understanding down below.